In this video, we'll be talking about odd functions and even functions. Now, I personally don't like the placement of this lesson in the textbook because really, when we talk about odd functions and even functions, it's not strictly reserved to the conversation of polynomial functions. You can really talk about odd and even functions anywhere you want, but because the focus in the unit is on polynomial functions, most of the examples we are working with in this lesson will be polynomial functions, but I really want to stress the fact that odd and even functions do not necessarily have to be polynomial functions. As long as they hold the properties which are required to be an even or odd function, then you're an odd and even function. Okay, so I'll go over that detail more in depth once I explain to you what an odd function is and what an even function is. So, you know what? Let's start off by talking about an even function. An even function is any function that is symmetrical about the y-axis. So if you look at our original parabola we learned in grade 10, that function is an even function because if you take a look at it, that displays line symmetry about the y-axis. Now that's beautiful. So graphically, we can determine whether a function is even or not. But unfortunately, we want to generate an algebraic test. We want to test by using the equation instead of using the graph to determine whether the function is even or not. Okay, so what we're going to do is we'll look at this parabola, okay, as a visual aid to help us generate the algebraic test to determine whether a function is even or not. So it seems that whenever the point xy is on the graph, so I don't know, let's say this point is on the graph, then the point must also be on it. So this point here is 2, 4. And because 2, 4 is on the graph, guess what? To make sure, to ensure that you have line symmetry about the y-axis, the point negative 2, 4 must also be on the graph of this function in order for there to be line symmetry about the y-axis. If 2, 4 was on the graph and negative 2, 4 was not on the graph, then we certainly do not have line symmetry about the y-axis. Let's do one more example. 1, 1 for example. If 1, 1 is on the graph, then negative 1, 1 must be on the graph. So you can keep going on and on and on, but hopefully you can see a pattern. If you want line symmetry about y-axis to exist, then xy must, if xy is on the graph, then the point negative xy must also be on the graph. Okay? If xy is on the graph and negative xy is not on the graph, then guess what? We will not have line symmetry about the y-axis. So that is going to help us generate the algebraic test. So xy and negative xy, which means f of negative x equals f of x. When I let the input be x and when I let the input be x and when I let the input be negative x, guess what? They both generate y. So that's why this algebraic test makes sense. F of negative x as well as f of x should both give me y, right? So you can think of algebra from the graph. You can say if I go left by 5 units, I'll get the y value. If I go right by 5 units, I'll still get the same y value. So one more time, if I go right by 4, I get some y value. I go left by 4, I get some y value. So that's why we have f of negative x equals f of x. If this holds true, then we can say that the function is an even function. Okay, let's see here. So I'm gonna find f of negative x. Okay, and let's simplify this. 3x power 6 because it's an even exponent. Even exponent. Hey, it's exactly the same as f of x. So we're gonna say f of x. So f of negative x equals f of x. That's our conclusion. So guess what? Since of negative x equals f of x, we can conclude f of x is even. Now please don't confuse even function with, for example, even degree power function. They're totally different things. Don't confuse even function with even degree polynomial function. They're totally different, okay? So I don't want to confuse you, but an even degree polynomial function can be an even function, but not every even degree polynomial function is an even function, okay? A simpler way of saying that is some even degree polynomials have line symmetry about y-axis. All right, let's try B. I can tell you right off the bat that this function is not an even function because there's no symmetry in the zeros. One of the zeros is -2 and the other zero is 1. So because there's no symmetry in the zeros, I can already tell you this function is not even. It's always a good idea to look at the function and establish whether it's even, odd, or neither. Well, in this case, we're only proving whether it's even. It's always good to establish whether it's even or not. Because to be honest with you, most of the time, you can just look at the equation and already tell whether it's even or odd. But if the question, and most of the time the question will be, prove algebraically, you have to show your work. You can't just say, oh, I know it's even. So, f of negative x. So, every time I see x, I replace it with negative x. I factor out -1. So, I'll show all my steps here. So if you factor out -1, -1 times -1 would be +1. So all you're left with is x minus 2, x plus 1. And guess what? X minus 2 times x plus 1 is not the same as f of x. So since f of negative x is not equal to f of x, therefore f of x is not even. Okay? And what about this function, f of x equals x cubed minus x plus 1? Right off the bat, I can tell you this function is certainly not even. How do I know it's not even? Because it's a cubic. It's a degree of 3. And it's a positive leading coefficient, so the end behavior is quadrant 3 to quadrant 1. There is no way with that end behavior I'm going to get a function that has line symmetry about the y-axis. Not possible. But nonetheless, I'll show my work algebraically. But in my mind, I already know I can't possibly establish that this function is even. Okay, yep, certainly not the same. And as expected. So all degree polynomials will not be even functions, which makes sense based on the idea of symmetry. Okay. Now, back to the point I was trying to make in the beginning of the lesson. Like I said, in this unit, we're focusing on polynomial functions. So all the examples are polynomials, polynomials, polynomials. But to be honest with you, there are functions, many functions which are not polynomial and are even functions. Because all it takes to be an even function is any function that has line symmetry with the y-axis, or f of negative x equals f of x. So hopefully you can think of a function that you learned last year in grade 11 that displays line symmetry about the y-axis. So hopefully you can remember y equals cos x. The cosine function is an even function. The cosine function is an even function. Okay, so any function that displays line symmetry about the y-axis, that is an even function. Okay, so anyways, the cosine function is an even function. I just don't want you thinking that only polynomials can be even functions and odd functions. All right, So now that we know what an even function is, let's see if we know what an odd function is. Okay, so if an even function is any function that displays line symmetry about the y-axis, an odd function is any function that displays point symmetry about the origin. So once again, we want to generate an algebraic test. Okay, so hopefully you remember what point symmetry about the origin means. We talked about that first when we did the first lesson with odd degree power functions. And if you rotate the piece of paper 180 degrees, you get the same graph. So you know what? Let's say here, we're going to do the same thing we did last time. If the point 1, 1 is on the graph, and you want to ensure that there's point symmetry about the origin, what is the other point that must exist on the graph to obtain point symmetry about the origin? Hopefully you'll say the point -1, -1. Okay, if 1, 1 is on the graph, and this function has point symmetry about the origin, then the point -1, -1 must also be on the graph. Okay? And you can do other points if you want, but if the point x, y is on the graph, then the point -x, -y is on the graph. And because this is true, that means the algebraic test for an odd function, or to check if the function is odd, would be to check if f of -x equals -f of x. To check f of -x equals -f of x. So you can look at the 2 points and come up with this logic. But yeah, as long as this is true, then the function is odd. So we have a method to determine whether the function is even, and another method to determine whether the function is odd. And to be honest with you, most functions are neither even nor odd. Okay, so if it's not even, not odd, then we say it's neither. Okay, so let's work with these examples here. So for question 2, I have 4 functions, they're all polynomials. They ask me if the function is even, odd, or neither. So for all these questions, my approach will be the same. I'm going to check if it's even first by finding f of -x, and then I'll check whether it's odd. Now there are different ways to do this, but I find students have a hard time with algebra when I do some factoring. So I'll keep it the most straightforward way that I think minimizes the number of mistakes for students. Okay, so f of x. Before I do it, I'm going to tell you right off the bat, this can't possibly be even. It might be odd. In fact, it is odd, and I'll show you how I know after. But this is odd. It's not, well, it's certainly not even because it's degree 5. So f of -x. So this is to check whether it's even. But like I said, we already know it's not even. So this is negative, so it's positive. Okay, so it's not even. So now that I know it's not even, I have to check whether it's odd. So what you do here is you write -f of x. Okay, because you already have x here, you just have to take that, multiply by -1. And what do you know? -f of x is equal to f of -x. Now, because we can write that, we know that f of x is odd, right? Since f of -x equals -f of x, therefore f of x is odd. Now, how did I know right off the bat it's odd? Because this is a polynomial in standard form, and all the exponents are odd, and there's no constant term. So if all the exponents are odd and there's no constant term, then I know that this function is going to be odd. And it makes sense based on your knowledge of powers from grade 9, because all the signs of the terms will switch from positive to negative or negative to positive, because now the base is negative and it's an odd exponent. So using the exact same logic, if you look at b, I'm hoping you realize that this function will be even because all the exponents are even and based on your grade 9 knowledge of powers, then the terms will all remain the same. Okay, so if it's in standard form, we can actually just look at the exponents of the terms, and you'll know if it's odd or even. So f of negative x equals f of x, and since f of negative x equals f of x, therefore f of x is even. Okay, so for C, we don't have it in standard form, we have it in factor form. I can tell you right off the bat that this is certainly not odd because it's a quartic, it's a degree of 4, and I'm staring at it, I'm looking at the zeros, there's symmetry in the zeros, so I can tell you it's even, but I still have to do the work. Okay, but it's really good to establish what it is first so you know where you're going. Okay, so I would, if this was on a test or a quiz, I would just pause for a moment and just stare at it, and I know what I'm trying to prove. That's always helpful. So okay, so for every one of these factors, I'm going to factor out -1. And there are 4 factors, and if I factor out -1 4 times and multiply them, that becomes +1. So that negative stays there, and these negatives are all gone. So factor out -1 4 times, and guess what? The factors are identical. F of negative x equals f of x. And that means f of x is odd. Oh, sorry, is even. Okay. Okay, what about this one? I can tell you right off the bat, this one is odd. How do I know? First of all, it's a degree of 3, so it can't be even. And secondly, this function has symmetry in its zeros. So unfortunately, I didn't have any examples where the function is neither even nor odd, or even nor odd. But in the homework, there are a few examples where it's neither. Okay, so it's not even. And now I check whether it's odd. And it is. So since f of negative x equals negative f of x, therefore f of x is odd. And I will say one thing. For this first unit, I would argue that this lesson is the one that causes students the most trouble. I think it's just the most algebraically intense because the first few lessons, there wasn't much algebra to it. It was a lot of discussion in terms of properties and graphing. So this is really, I would say, the first lesson that required you to use your algebraic skills. Okay, last question. If f of 3 equals 6 and f of negative 3 equals 6, does this prove that f of x is an even function? So hopefully you're going to say no. Okay, so the question is why? We can't just say no. So let's say 3, 6, and negative 3, 6. Okay, just because you have a pair of points that demonstrate line symmetry about the y-axis, that doesn't mean the entire function, like the rest of the function, demonstrates line symmetry of the y-axis. So for example, I don't know how the rest of that graph looks like, but I'll make something up. Right? Clearly, this function is not an even function. Okay? So, yeah, we need f of negative x to equal f of x over its entire domain. Okay, not just for 3 and negative 3. So that's why some students, I put this question because some students, they do something quite silly. If I ask them whether the function is even, they just do a single test value like f of 1 and f of negative 1 and show that they're equal, and then they conclude that f of x is even. But you can't do that. Just because it happens once doesn't mean it's going to happen every single time. So unfortunately, if you want to prove a function is even, you have to have a very general test like f of x and f of negative x and showing them to be the same. Okay, so that's even and odd functions.